White light is made of all the wavelengths in the visible region of the spectrum. In other words, all the colors. When white light passes through a prism, the different wavelengths are bent at different angles. Thus, the wavelengths are separated, and we can see the different wavelengths or colors. This is called a continuous spectrum. All the wavelengths of the visible spectrum are present. But something interesting happens when a gas is charged with energy. Let's use the simple example of hydrogen, H2. When a chamber of hydrogen is subject to high voltage electrical discharge, the molecule dissociates into hydrogen atoms with high energy. These atoms relax by emitting energy in the form of photons, or emitting light. Interestingly, after passing through a prism, the resulting spectrum is not continuous, but rather only single discrete lines appear, almost as though the emitted photons are quantized. This is called an atomic emission spectrum, or line spectrum. This is true for all elements, and each element has its own unique emission spectrum. In fact, a common chemistry lab is identifying elements based on their emission spectrum. Here are the examples of hydrogen and helium. Quite different. We'll focus on the hydrogen spectrum for this discussion. There are even lines in the higher frequency, higher energy UV region, and the lower frequency, lower energy IR region of the spectrum, but our human eyes cannot see those lines. These emission spectra have been known for many years, and scientists try to find a reason why only lines appeared, and in the same pattern, where the lines seem to converge to a limit. Let's start with Johann Balmer. In 1885, Balmer found an interesting connection as he used this equation. Frequency is equal to a constant times 1 over 2 squared minus 1 over n squared, and plotted the frequency of the emitted photons versus 1 over n squared. The graph shows a linear plot. The equation of the line is called Balmer's equation. There's an interesting caveat to Balmer's equation. In the term 1 over 2 squared minus 1 over n squared, n must be an integer value higher than 2, starting with n equals 3, 4, 5, etc. For example, when n equals 3, the frequency corresponds to the yellow emitted photon. N equals 4 corresponds to the teal emitted photon. And here are n equals 5 and n equals 6. Balmer's equation also accounts for the convergence phenomena of these lines. As n increases, the difference in 1 over 2 squared minus 1 over n squared decreases, explaining why the lines in the spectrum converge. Let's pause to appreciate this truly amazing and rather simple conclusion. The main point is that Balmer showed that these frequencies of the photons emitted were differences in whole number integers. 2 and 3, 2 and 4, 2 and 5. This is called the Balmer series. Indeed, shortly after Balmer's work, others showed series in other parts of the spectrum. Notice how they all show a correlation with whole number integers. Johann Rydberg showed that all these lines were related by the equation frequency is equal to the Rydberg constant times 1 over n1 squared minus 1 over n2 squared. So this begs the question, why would the emission spectrum of the hydrogen atom follow such a simple pattern of differences in what would appear to be whole number integers? Again, it appears that the allowed values are quantized. Why would hydrogen care about our whole number integers and quantized energy? For this, we turn to Niels Bohr and his proposal of the quantum mechanical view of the atom.